So let's dig a little deeper into growth and decay models and take a look at where they come from and how they behave. So let's see here. So the basics are that if we're going to let P be the population at time t, and then we're going to let beta be the birth rate, and delta be the death rate. And so both of these are going to be given in terms of number of organisms per time period, so per year or per hour, depending on the species that we're looking at, something like that. So then the idea is that during a short time period, and let's call the short time period delta t, then the number of new arrivals we have, well, we're going to have beta times population size times time interval births, and we're going to have delta times population size times delta t deaths. Okay, so if we look at the amount that the population has changed in that time interval, this is going to be approximately equal to beta minus delta. So we're just looking at the difference. So the new ones minus, sorry, the newly appearing ones minus the ones that are disappearing, times pt delta t. And then I can divide the delta t over to the other side and look at delta p over delta t as, and let's see, on the left, we're going to, or sorry, on the right, we have beta minus delta times p. And then I'm going to take the limit as delta t goes to 0 of both sides. And so now there is actually no delta t over on the right-hand side. So the that's just a constant function with respect to delta t. So I'm taking the limit of both sides, but on the right side, it kind of doesn't matter. On the left side, however, that expression is exactly p prime. And now you notice I'm writing an equality instead of an approximately equal to, because in the limit, when you take the limit rather, then you actually do get something that's equal. And so quite often we say that p prime is equal to kp, where k is birth minus death rate. And so this is the net rate of change of the population. Okay, and so to solve this one, multiplying across using the usual rule for separable equations, and then integrating, oops, let me change back to black. We get log of p is equal to kt plus a constant. And by the way, at this point, from now on, I'm going to write log for natural log, just because people standardly use log to denote natural log after calculus. So let's see. So then I will exponentiate both sides of this equation right here. And so this gets me p is equal to c e to the kt. And if I evaluate this at t equals 0, then I get p of 0 is equal to c times e to the 1. So I can actually write that p is my initial population times e to the kt. Okay, so that's the derivation and solution of the standard exponential population model. We have a couple of ideas that go along with this. So there's some properties that sort of characterize exponential growth and decay. And so that is that if k is positive, then we say the doubling time is the time interval tau, such that if we increase the time by tau, then we double the population. And for negative k, the half-life is going to be the time interval tau, such that if we allow that much time to elapse, then we end up with half of what we originally began with. And so it's a key property of exponential functions that they actually have doubling times and half-lives, and that it doesn't matter when you begin the time interval. So this t here, if you have a positive k, there will be a doubling time, and it will be independent of the time that t that you start at, and same for half-life. So let's see. So to find the doubling time, we look at when the population has doubled. So that's twice what it started as, so 2 times p of t. And this is supposed to equal the population evolved forward by time tau. So using the formula that we found, this would be ce to the kt plus tau, or ce to the kt e to the k tau. Now, looking from the beginning of this equation to the end, we can cancel off the ce to the kt and the ce to the kt, and we're left with 2 equals e to the k tau. So taking logs of both sides, we have this, and then dividing by k, we see that the doubling time is 1 over k log 2. And then for the half-life computation, it's exactly the same, except that the sign of k is different. So to find the half-life, we end up looking at where 1/2 p of t is equal to p of t plus tau, and going through the same steps, we find that tau is equal to minus 1 over k log 2. And that's actually a positive number, because this is the situation where k is a negative number, and so this entire quantity right here is going to be a positive number.